So my name is Filip, and this is a session in which we are not going to learn anything particularly useful. But at the same time, we will try to answer a very deep question, and that is, what is the true meaning of reality? And if you think about it, this is probably the most important question that you could ask as a human being. So from that perspective, I hope that it will be at least moderately interesting. At the very least, I hope that this will not be an hour of your life that you will consider to have completely wasted. Now, first of all, thank you all for coming. I really appreciate it. I really do, especially as this is the last slot for today. In fact, this is the last slot for the whole event, which is a perfect time to talk about a lightweight subject like this. So the idea for today is as follows. We will look at several experiments from the field of quantum physics, experiments that actually allow us to experience firsthand some of the most bizarre quantum phenomena. But of course, we are not in a physics lab, but we are software developers, so that's what we will use to our advantage. So what we will do is we will try to reconstruct those experiments in the code using a quantum programming language called Q#, although the examples will be quite simple, so don't worry if you have never dealt with Q# before. And then we'll try to sort of reason about this and see sort of what is going on, right? Because as developers, we are used to modeling things in code, we are used to reasoning about problems in code, we are used to exploring new domains by looking at the code, and that's what we'll try to use to our advantage. So hopefully it will work out. Now, quantum physics, of course, has a reputation, right? So we have a motto for today, this wonderful quote from Niels Bohr: everything that we call real is made of things that cannot be regarded as real. And hopefully, as we go forward with this session, you will actually start to agree with Mr. Bohr. There's actually a reading list that goes with this session. It consists of these 3 books. And even though they look very similar because they are all from Springer, they're actually from 3 separate fields. And so the first one is a quantum computing book. And there are actually many much better quantum computing books than this one. But this one's mine, so that's why it's included. The second book is actually the best introduction into quantum physics that I know of. And then finally, there is a book about the philosophy of the whole thing. And today we are going to be sort of sitting at the intersection of these 3 fields: quantum computing, quantum physics, and philosophy. What else? So this is the company that I work for. I'm actually based in Switzerland, so I flew in here from Zurich. Although I do have quite a deep relationship with the UK. I went to university here, although here means actually in Scotland. And the first thing that they taught me there was that you're supposed to hate London, so there you go. That's all with the taxpayers' money as well. All right, so let's start by looking at a little bit of a historical background just to set the stage. So quantum physics as a field dates back to year 1900 when Max Planck introduced the concept of quanta. I mean, he didn't call it that way, but that's when the concept was born. And he was working on a problem that was called the black body radiation problem. And basically, in order to fit together the experimental data and the mathematics of the whole thing, he no longer could treat energy as this sort of continuous, free-flowing thing. Energy had to come in discrete packets. And that's when the concept of quanta was born. And these packets were incredibly small. And we see here the Planck constant. It's an incredibly small number. In fact, if we'd like to imagine how small the number is, we could sort of take our human scale as a starting point, so 10 to the power 0 meters, like 1 meter. Then the highest scale that we can go up would be the size of the observable universe, which would be about 10 to the power 26. So 26 orders of magnitude. But in order to go down to the Planck scale, we have to go down to the 10 to the power minus 35, right? So it is actually much further. A Planck constant is going to come back in some of the later slides, so for now we leave it. But this is when the revolution was started. And for about 25 years that followed, physicists tried to unsuccessfully model an atom. And the reason why they were unsuccessful was that the idea of an atom at that time was, and I think it is still in the heads of many people because it's just such a useful analogy, was that an atom is sort of like a mini solar system, right? Like with the nucleus at the center, like a little star, and then electrons like little planets swirling around. But actually, you cannot model this with classical equations of motion. It's just unstable. Such a model just sort of collapses in on itself. And the breakthrough came in year 1925, when Werner Heisenberg, he was only 23 years old at the time, he basically ditched classical mechanics in favor of a completely abstract mathematical model that was based on something that we call observables. And we are going to talk about observables in a moment. But in principle, he focused on that these are actually literally Heisenberg's words. He focused on quantities that are in principle observable. And we will see in a moment what this means, but this is when quantum mechanics was born. And quantum mechanics is one of the most successful scientific theories of all time, maybe the most successful one, because it has allowed humanity to go on an absolutely unprecedented growth path, right? It has propelled our civilization on a growth path that was never seen before. So just about any artifact that we associate with a highly developed civilization is really only there because of our ability to master quantum mechanics. Without quantum mechanics, there would be no transistors, no computer chips, no semiconductors, no superconductors, no GPS, no MRI scanners, no modern material science, no modern medicine. Just about anything that is out there that is high tech is only there because of quantum mechanics. At the same time, quantum mechanics is also very, very strange. And Richard Feynman, probably, well, maybe not the greatest, but one of the greatest physicists of the 20th century, he famously said that nobody understands quantum mechanics. And Feynman himself, of course, won the Nobel Prize for his work on the quantum theory in the 1960s. The major problem with quantum mechanics, and this is in a way the fault of Heisenberg, is that it doesn't provide an objective description of reality because of the fact that it focuses on those observables. So it basically tells us what happens when we interact with quantum objects, when we look at them or when we measure them, or as the name suggests, observe them, but doesn't really tell us what is happening in between. So if we wanted to sound smart, we would say that quantum mechanics lacks ontological character. And Niels Bohr, and he's the most quotable physicist of all time, he summarized this by saying, there is no quantum world, there's only an abstract quantum mechanical description. Right? So quantum mechanics is basically a mathematical toolbox that leaves a lot of room for interpretation of what is it actually describing. So Niels Bohr is, he was a physicist, but he was also a philosopher. That's why a lot of things that he said were very deep. So this was actually translated into a more understandable language by David Mermin, a contemporary physicist, who actually summarized this by saying, shut up and calculate. And basically, this is what most physicists have been doing over the past century, and with great success, right? Because quantum mechanics has been very successful. All right, so let's now start looking at some of these quantum concepts. The first one that we'll tackle will be the superposition. And in order to appreciate superposition, we will look at the device that is called the beam splitter. And as the name suggests, the beam splitter can split a beam of light into two beams of light. So I can take a laser, I can shoot it at the beam splitter, and the two beams of light will exit the beam splitter, and one will travel towards detector 1, the other towards detector number 2. So I think there's nothing particularly dramatic about this, and it is a common device used in optical physics, beam splitter. Now, light is an electromagnetic wave, like electromagnetic radiation, and behaves like a wave. And this is something that we have known since the 19th century. At the same time, light is also made of particles, the so-called quanta of light, or more commonly known as photons. This is actually something that was shown and proven for the first time in 1905 by a gentleman that you might have heard of. His name was Albert Einstein, and he actually won the Nobel Prize for that work. So it was not for relativity, but it was actually for describing the so-called photoelectric effect. So actually what I can do with my laser is I can turn down the intensity of the light very, very far down. In fact, so far down that I will be emitting individual photons towards the beam splitter. Now, an individual photon is something that we cannot see anymore, but we can detect the arrival of the photon at the detectors. That's why I guess they are called detectors. So if I shoot a single photon at the beam splitter, what I would actually see is I would see that one of those detectors randomly flashes and records the arrival of the photon. And then if I keep repeating this, it will sort of start to average itself out. So basically, 50% of photons will arrive at detector 1, and 50% of photons will arrive at detector 2, which in a way ends up reproducing the same effect as a continuous beam of light. So if we try to explain what the photon is actually doing, the logical conclusion would be that the photon hits the beam splitter, and it sometimes goes one way, sometimes goes the other way, and it over time averages itself out. Now that's actually completely wrong, but for now it actually fits the experiment, right? So what we can do is we can actually very easily model this in Q#. So here I have, is this large enough or too small? Okay. So I basically have here a piece of code. Actually, I have it here first, so maybe let's look at it here. So this is a Q# operation. And what I'm going to do is I'm going to first allocate a quantum bit, a Q bit. And this will be our photon. And then we have to model the beam splitter. And we model it using the H transformation, which is an instruction that is available in every quantum computer and also in every quantum programming language. We will see in a moment what H actually really does. But for now, we just say that this is a rough estimation that is good enough to model a beam splitter. And then what we will do is we will model the actual detectors. And we do this by performing a measurement over the quantum bit, so in our case, the photon. And the measurement basically extracts a classical bit out of a quantum bit. So it gives us a 0 or a 1. And that is, of course, something that we can then map to detector 1 or detector number 2. And so this is the code that I had on the slide. I'm actually running this on a simulator because it is a bit more reliable than trying to run this on a real quantum computer. And I'm going to repeat this 1,000 times, right? And if I now run it 1,000 times, what we get is we get 500 zeros, roughly, and 500 ones. And this is exactly what we would see in the lab with the beam splitter and individual photons, right? So there's nothing particularly exciting about this. But things become very weird once we start stacking the beam splitters one after the other. So now we have an updated setup. And this device is now called the Mach-Zehnder interferometer. We have a beam splitter. And so the laser shoots a beam of light at the beam splitter. The two beams of light now go sort of outwards like before. But instead of being captured by the detectors, we have a pair of mirrors that reflect the two beams of light, and they are redirected inwards towards the second beam splitter. And now what is interesting, if you look at these arrows here, no further splitting is happening in the second beam splitter. And the reason why no further splitting is happening is because of the interference effect. That's why this device is called the interferometer. And interference is something that is a behavior exhibited by all kinds of waves, right? So waves on the surface of water, sound waves, and of course light as well, because light is an electromagnetic wave. And so in this case, what we can say is that the two beams of light effectively interfere with each other. And because of this interference effect, how the beam of light exits the second beam splitter is only towards detector number 2, and no further splitting is happening. And we can actually explain all of this using 19th century physics. We don't have to invoke any quantum concepts to actually explain this, because again, interference is a typical behavior of waves. Now, problems sort of start to mount once we send a single photon through this device. Because if I send a single photon, then we can maybe try to reason what is going to happen. So I'm going to annotate this. And if we imagine that I now send a single photon at the beam splitter, right? Remember, we cannot see a single photon. We would only see the arrival of the photon at detector 1 or detector number 2. Just moments ago, we said that if the photon hits the beam splitter, it appears that it will randomly go one way, randomly the other way, and things will average out. So let's imagine that the photon went here, right? And it sort of gets reflected, and then it hits the beam splitter. And now the logic breaks down, because of course if the photon hitting a beam splitter should randomly go one way, randomly the other way, then we should see some photons go here, and some photons go here, right? But in reality, when I run this in the lab, I would always see every single photon arrive here, even if they are individually sent through this device. So how could that be? How can we actually explain this behavior that basically here the photon appears to behave differently, and here as well differently? So actually quantum physics is very happy to provide an explanation, but it's actually an explanation that comes at a very high price, because it actually disrupts our understanding of how reality works. So this is what quantum physics tells us. When the photon approaches the beam splitter, it sees that there are two paths that it can take. It can take the upper path in the interferometer or the lower path. And because nobody's looking at it, it takes this path and it takes this path at the same time. And then it approaches the second beam splitter effectively from two separate directions. So it ends up interfering with itself. And because of this interference effect, it exits only here. And that's why here we actually get every single photon arriving at detector number 2. So again, we now have an explanation of what is going on, but effectively we have to accept that somehow the photon is in 2 places at the same time. Now we can model this very easily in Q#. We can simply add a single line of code to our existing code. We have our photon, that's a Q bit, a quantum bit. We then have a beam splitter, that's the H transformation. And then we have a second beam splitter just immediately after that. And when we then perform the measurement of the Q bit, we will actually get only zeros, just like in the lab. So basically, sticking 2 beam splitters one after the other would create interference. And so if I now run this piece of code, and I run it 1,000 times, we now get 1,000 zeros only. So effectively, all the photons arrive at only one of the detectors. So that was really weird, right? Because again, the explanation here is a bit suspicious that the photon somehow is in 2 places at once. I mean, this is not something that we experience in our everyday macroscopic reality, right? So like I'm here in front of you, which means I'm not there somewhere in the pub at the same time, right? Which again would be very convenient, but we just don't see these types of effects. So it's really weird. But the thing is, it actually gets weirder. Because if the photon is really in 2 places at once, well, let's just improve our detection mechanism, right? Let's just stick detectors along these 2 paths in the interferometer, where supposedly the photon is simultaneously or at once. And we basically could try to catch the photon being in 2 places at once. And we should surely be able to outsmart the photon, because, I mean, we have a brain, right? And the photon, I mean, it doesn't even have a mass. So this is the updated setup. We've now added these sort of brown thingies here. And these are the so-called quantum non-demolition traps. And these are basically detectors that do not destroy the photon, but just allow it to continue. But as soon as we stick those quantum non-demolition traps, weird things happen. So let's sort of annotate this. So the photon travels here towards the beam splitter. Then we said, OK, at this point, it takes these 2 paths, right? So it's here, and it's here. And now we try to capture the photon being in 2 places at once. But as soon as we try to do that, the photon will randomly decide I'm here or I'm there, actually with 50% probability. So it will sometimes light up detector or quantum non-demolition trap 1 and sometimes the other one. It will never sort of be caught in 2 places at once. So let's imagine that it showed up here. Right now we know that it's there, which means we have forced the photon out of the superposition state. And now it approaches the second beam splitter, and it actually approaches it only from one direction, not as before. So it doesn't have itself to interfere with anymore. So the interference effect disappears. Instead, what happens in the second beam splitter is exactly the same thing that happened in the first beam splitter. Namely, the photon enters, again, and this is what we call the superposition state. So it basically takes both of these 2 paths, right? And it travels along those 2 paths happily until it tries to be observed, in which case, randomly, one of the 2 detectors is going to detect the photon, right? So it's either here or here. So in other words, the photon behaves differently depending on whether we look or not, which, if you think about it, is very troubling because it actually tells us that there is no such thing as an objective reality, right? We simply change the outcome of the experiment by just adding a different way of looking at the system that is being experimented with. Now, we can very easily model this in Q# by simply adding yet another line of code to our existing program. So we have a photon. This is our qubit. Then we have the beam splitter. And instead of having a second beam splitter immediately, we will model the quantum non-demolition traps. And we will do this by doing a measurement. So we will basically be asking what is the current observable state of the qubit, in which case it will produce a 0 or a 1 randomly. And the rest of the program stays the same. And so the net result is that we should get a random 0 or 1 here. And we should get a random 0 or 1 now here, because the interference effect actually disappears. And what we are now returning from this program is we are returning the quantum non-demolition result and the detector result. And the first bit here, right? That could be a 0 or 1. It's actually equally likely, and it's the same here. So actually, we have 2 bits that this program returns, and each combination, each of the 4 combinations is actually equally likely. And this is what we should see in the code. If I run this code, this is exactly what I get, right? And so this is exactly what we would get in the lab as well. So if I come back here, we would see these quantum non-demolition traps randomly flash, and then these guys would also randomly flash. Again, the outcome of the experiment changed by simply looking at things. And this is what we call superposition. The superposition is simply the photon that appears to be really in 2 places at the same time. Now, mathematically, it's not super complicated. So let's have a look at the sort of high-level mathematics. So mathematically, the state of a simplest quantum system is described by a vector. And the vector is alpha over beta, where alpha and beta are complex numbers. And there is only one condition that they have to fulfill, namely, if you take absolute values, you square them, you add them, they have to be equal to 1. And that's basically this. So we'll see why this matters in a moment. The thing is that, just like we said in the beginning, when Heisenberg introduced observables, it basically allows us to see the quantum system through the lens of an observable, but it doesn't actually allow us to see the quantum system in between. So this actually means that we cannot ask a quantum system an objective question, what state you are in. We cannot ask, what is your alpha and what is your beta, right? We have to choose an observable first, and the observable actually restricts the states that are visible to us. So here are a couple of observables. We will mostly work with the top one because it's mathematically the simplest, the Z observable. Observables are represented by matrices, and each of those observables has a pair of states that we call eigenstates that are the states that can be observed using this observable. So in this case, it's alpha equal 1 and beta equal to 0, and vice versa, right? Alpha equal to 0 and beta equal to 1. And basically, these are the only states that we can see in a quantum object if we use the Z observable. So what does it mean? So it means that if I would like to interact with a quantum object, I have to approach the quantum object. I have to say, I have chosen the Z observable to interact with you. The Z observable gives me 2 observable states, 1 over 0 and 0 over 1. Which of these 2 states you are in? And the quantum object might be in one of those 2 states, in which case it will actually deterministically answer, thank you for asking, I'm 1 over 0, or I'm 0 over 1. But actually, the quantum object can be in one of infinitely many other states where basically alpha and beta would be both non-zero. Right? So the way you can picture this is like this iceberg, where at the tip of the iceberg you have the observable states 1 over 0 and 0 over 1. These are the only things that we will ever see. But the quantum object can actually be in many different states. And mathematically, we express all these other states as a linear combination of the observable states. And this is what we see here at the bottom. And this is what we call superposition. Right? And now the interesting question is what happens if the system is in a superposition, right? And then I show up with my 2 observable states and I'm asking, are you this or are you that? And then the system undergoes what we call a quantum state collapse. So basically it changes its state to one of the observable states. And this is probabilistic. We can calculate this using the mathematics of quantum mechanics. But this is also why we say that there is no such thing as an objective reality, because actually reality gets sort of created at the moment of observation when the quantum state collapses. And this is how we can now annotate what is happening in this Mach-Zehnder interferometer. So the system starts in one of the observable states, because we shoot a photon out of a laser, so we know what state it is in. As soon as it goes through a beam splitter, it enters a state where basically alpha and beta are both non-zero. So it's now in a linear combination of both of the observable states. So we don't know whether it's here or there. So it's actually in both at the same time. And then as soon as we try to look at it, we apply the Z observable. So the system is forced to choose. And it chooses to be, for example, here, which then gives it a certain observable quantum state. And then in the second beam splitter, the same thing happens. And then in the detector, again, the same thing happened as in the quantum non-demolition trap. Right? So it's all very strange, right? But the consequence is that actually the default state of reality is a sort of fuzzy, blurry thing. And only when things are observed or measured, they actually acquire certain states. And this, of course, leads us to the most famous paradox in all of physics, and that is the cat of Erwin Schrödinger that was both dead and alive at the same time. And so this is the experiment that Schrödinger imagined. He imagined, and this is a natural consequence of the concept of superposition, of course. He imagined a radioactive atom, like an atom of polonium, and the radioactive atom will radioactively decay at some point. And actually, that event of a decay, that is a quantum event, it is governed by the rules of quantum mechanics. We can actually calculate the probabilities involved there. Now, for our purposes, we can say that there are two observable states, right? There is an observable state of a no decay and another observable state where the decay happened. But what quantum mechanics tells us is that when nobody is observing this system, then the atom will be in a superposition of both decay and not decay. And then, I mean, you probably see where this is going, right? Because then Schrödinger imagined, okay, let me connect it to a Geiger counter. The Geiger counter will detect the decay of an atom. And when it detects the decay, it will release a poison into a box, and there is a cat in the box, and then the cat will immediately die. And of course, his argument was that when nobody is observing this system, then it means that the atom is in a state that is both decayed and not decayed at the same time, in a superposition, which means that the poison is both released and not released, which then means that the cat is both dead and alive. And actually, it's a logical sort of reasoning, right? And we can model this in Q#. So we have it here. And we will start by modeling the polonium atom, like Schrödinger imagined. And we will use a qubit as our atom, and we will then place the qubit into a superposition using this type of a sort of a rotation. Now we could use an H transformation here because we already know that an H transformation actually created a superposition, but it actually creates a so-called uniform superposition. So once you apply an H to a qubit, it's actually equally likely to undergo a quantum state collapse to a 0 or a 1. But actually, that's not what we want. Here, we want a more subtle superposition where it's like 90%, 10% for the two outcomes, right? So it's 90% likely to not decay and 10% likely to decay. And if I run this 1,000 times, this is what we are getting, right? So in 900 cases, the outcome of the program is 0, so no decay happened, and otherwise there's a decay. And now let's connect a cat to this. And this is where we have to squint our eyes a little bit because the modeling sort of capabilities are limited, because we cannot model too many qubits because it's computationally too intensive. But for our purposes, we will imagine that the cat it consists of two particles, right? So we will model the cat with two qubits, like the front of the cat and the back of the cat. And we are basically going to connect the cat to the atom. And we do this by applying the CNOT instruction, which is, again, a fundamental instruction in quantum computers. And it's basically a form of a copy, right? It's a controlled NOT. And basically what it does is it looks at the first qubit, and if that becomes a 1, then that value is copied into the second qubit. Otherwise, nothing happens, right? The default state is 0. So it's a way of copying a state from one qubit to another. And this is very useful for our modeling use case because, of course, if the atom becomes a 1, that means that it has decayed. So we want to kill the cat, so we want to flip the cat to a 1, 1 as well. Otherwise, the cat will stay at 0, 0. And so now we return this from this program, and we will get we have 3 qubits, so we can get 2 to the power 3, 8 possible outcomes, right? But in reality, we only ever see 2 of them. And if I run this, you can see that I get either 3 zeros or I get 3 ones. And so, of course, the first one, that's the atom. So if the atom doesn't decay, the cat stays at 0, 0 and doesn't die. Otherwise, the atom flips to a decayed state, and that kills the cat. And that is basically what Schrödinger imagined. Now, how can we resolve this paradox? There's a resolution to the paradox, although it's probably not super satisfactory. And the answer is that technically the logical reasoning in the paradox is correct. But in reality, large objects like a cat, which consists of probably 10 to the power 26 quantum objects or atoms, it's basically impossible to keep such an object in a superposition state for longer, or at all, pretty much. And the reason for this is that, I mean, there are two reasons. So first of all, in order to truly, completely isolate this from the environment, and when we mean environment, we really mean everything. So any sort of loose photons that are representing the light here, any molecules that are out there, any sort of free particles that are whizzing around here everywhere, we would probably have to place this whole system in a vacuum. That would anyway already kill the cat. We would have to cool it down to an absolute zero, or close to an absolute zero. That would anyway kill the cat, right? And so on. The second problem is that the cat itself would also emit particles, right? Like thermal heat and so on. And so we can model this, and then hopefully it will make a bit more sense. So in order to actually model this, we are going to add some particles that are going to represent the environment. So whatever is out there, right? And in this case, we are throwing in 5 additional qubits, and we are basically going to intertwine them with the system the same way as we intertwined the atom and the cat. And now the final outcome here, we basically have 8 qubits, right? So that will give us 8-bit results. So I should have 2 to the power 8, 256 possible outcomes. But in reality, just like before, I only get 2 of them, right? So if I run this 1,000 times, I get 8 zeros or I get 8 ones. What does it tell us? Well, it tells us that, remember the first one, that's the atom. Then the second and the third one, that's the cat. The rest is sort of loosely considered anything that is in the environment, any particle that is out there. And as soon as we know the value of one of them, then the quantum state has collapsed because we know the value of all of the other ones. And the way you can think about it in a sort of software analogy is that basically the surrounding environment, because it's never possible to truly isolate yourself from the environment, the surrounding environment is sort of like constantly logging the state of the cat in this experiment. And therefore, the quantum state basically collapses super quickly. So this just happened last week. There was a paper in Nature where scientists at the University of Vienna created the largest superposition state ever. And it actually consisted of about 7,000 atoms, right? And for that, they actually cooled them down to, I think, minus 176 Celsius. And the superposition was maintained for 12 milliseconds, right? And the cat would consist of, like we mentioned, about 10 to the power 26 atoms. So it's just, the paradox is sort of correct, but the sheer scale of the objects involved just basically prohibits this from happening in real life. Or when it happens for really like 10 to the power minus 25 seconds, for example. So that was the cat that was dead and alive at the same time. The next thing that I wanted to talk about is the uncertainty principle. And in order to talk about uncertainty principle, we have to introduce an extra quantity that is called spin. And it's a purely quantum property, so it's difficult to create an analogy in our everyday macroscopic world. But it is basically a form of angular momentum. And mathematically, it's described by a spin vector that we see here that has components in each of the three directions in a three-dimensional space. So there is an x, y, and z component of the spin. And in each of those directions, the spin component can only have a value 1 or minus 1, which makes it a perfect, actually, quantum object. And so we typically denote them with symbols. So in the z component of the spin, for example, we would not say 1 minus 1, but rather up and down. And then in the x direction, we would say like left or right or plus or minus. We are actually going to use only these two. So now we have an experimental device that is called the Stern-Gerlach apparatus. And it starts with an electron source. And we are going to emit an electron towards a silver screen. And as the electron travels towards the silver screen, it goes through a magnetic field that is created by a pair of magnets. And those magnets are actually sort of stacked on top of each other in this case. And because of this, the magnets basically form a Z observable because they can only deflect the electron up or down. So effectively, they form a Z observable, that is asking about the z component of the spin. It's asking, is your spin up or is your spin down? And if we prepare an electron with the z component of the spin to be up, then as we sort of shoot those electrons through the magnetic field, all of them will be redirected up, right? Because that is what we were expecting all along. However, I can rotate those magnets, and I can now place them sort of horizontally. What now the magnets can do, they can only deflect left or right. So the magnets now become an x observable. And if I now prepare an electron with the z component of the spin being up, but I don't prepare anything for the x observable, so the x component of the spin, then as the electron goes through this x observable, it's confused. It doesn't know what to do, so it will randomly go one way, randomly go the other way. So it randomly says I'm plus or I'm minus. There's nothing super problematic about it yet, although you might wonder that it's a bit strange that it actually acquires a value, again, by simply being looked at. But we will see in a moment that this is not the biggest problem with this. We can model this, however, in Q# very easily. Again, we just need about 3 lines of code. We will allocate a new electron, and this will be our qubit, right? So the default state of a qubit is 0, and we will just treat it as a z component of the spin being up, because we are free to choose how we model. And then we perform an observation. And so far, we were doing all these measurements in Q# code using the defaults of Q#, which is always the z observable, or as it's called in quantum computing, the z basis. But we can actually switch between the observables or between the measurement bases, and this is something that we can parameterize, right? And this is done here. So as long as we use here the z observable, so the z measurement basis, we will get a deterministic result. Otherwise, we will get a random result just like it was in the Stern-Gerlach apparatus. So if I now run this, we should see exactly what we discussed. So this is the piece of code that I had on the slide. If I run it 1,000 times, and I use the z basis, the z observable, I will get 1,000 ups, right? Because I'm basically asking a correct question to the electron. However, if I ask an incorrect question, the electron gets confused and produces a random outcome. So I get a plus or minus, and that is also exactly what we would see in the lab. But things become even more problematic once we stack 2 Stern-Gerlach apparatuses one after the other. And this is actually shown here. So we start with an electron, the z component of the spin being up. We send it through an x observable, so it's deflected left or right, in which case it randomly answers I'm left or I'm right, I'm plus or I'm minus. This we already established. But then we stick another pair of magnets there, this time oriented as a z observable, so it deflects up or down. So it's now asking, but what is your z component of the spin? And we should expect that in here and here at the bottom, we would get an up as a result, because that's how we prepared the electron originally. But in fact, this doesn't happen. We also get a random result then. And this is super problematic, because actually it means that the electron lost information simply because we looked at it wrongly. You can think of it as a sort of security that is built into the very fabric of reality. You could encode some information into a quantum object, but you will only be able to read it once, right? If you read it incorrectly, you'll destroy this information, which is effectively what is happening here. And this is a fundamental concept of nature. And actually, this is something that underpins the entire field of quantum cryptography. So this is how we can model this in Q#. Our qubit is the electron, and we simply stick 2 measurements one after the other. First in the x basis, so using the x observable, then in the z observable. And that's basically that. And then at the end, we return just the outcome of the second measurement, because that would help us illustrate what is going on. So this is this piece of code. I'm going to comment out this, and let's see what happens. So I start with the electron in the state with the z component of the spin being up, and I'm simply measuring in the z observable. And of course, in this case, I get 1,000 ups. But as soon as I add this additional line of code, where I simply ask about the x component of the spin up front, you'll see that this secondary measurement now becomes random. And this is exactly the same thing that we would see in this lab setup that we discussed. And this is what is called uncertainty principle. There's simply, according to quantum mechanics, there exist pairs of values in nature that you simply cannot know at the same time with arbitrary precision. So in this case, if we know the z component of the spin, we are forbidden by the laws of nature from knowing the x component of the spin and vice versa. This was developed for the first time in 1927 by Heisenberg. And he did this for position and momentum. And actually, what does it mean? It means that we either know where the quantum object is, but then we don't know how it is moving, or we know how it is moving, but then we don't know where it is. It's just prohibited by the laws of nature. And even more dramatically, there exists an uncertainty relation between energy and time. And you can see here that we have a Planck constant here. Actually, this is the so-called reduced Planck constant. And so this already implies that there are very small numbers involved here. But actually, to appreciate energy and time uncertainty, you should imagine an empty region of space, like something that is completely, truly empty. Right? So we would remove everything from it, all the molecules and the dust and the particles, and really there's nothing. It's vacuum or void or however you want to call it, right? Then if I ask you what is in there, then well, you say nothing because it's just the definition of it. And that's true. And then if I ask you what is the energy in there, then you would say, well, zero, because there's nothing in there. And that's also true, but only on average. Because as it turns out, because of this uncertainty relation between energy and time, once you take a tiny, 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 tiny slice of time, you now have such an unbelievably precise knowledge of time that you actually completely lose all the confidence in energy. And at these tiny, tiny time slices, so we are talking about 10 to the power minus 22, 24 seconds and smaller, the so-called virtual particles, they appear out of nothing. Like, it's sort of like the closest that we can think of compared to a God moment of creation. Like something appears out of nothing. And they always come in pairs, and then they immediately annihilate themselves. And when they do, they release energy. And this is the energy that they used to create themselves in the first place. And so at this time scale, the arrow of time actually sort of loses its meaning. And we know this is true. This is not some sort of a mathematical trick or a consequence of the mathematical formalism, because we can actually detect it. And this is what we call quantum fluctuations. So we cannot see the individual virtual particles. We are actually precluded from seeing them effectively by the uncertainty principle. But the cumulative effect can be detected using something that we call the Casimir effect. But the fundamental idea behind it is exactly the same idea that we studied with the spin and the fact that we cannot know the spin in the z direction and in the x direction at the same time. And it's all because of uncertainty principle. All right, the last topic that I want to cover is entanglement. And it's actually the weirdest of all. We sort of touched upon entanglement. I didn't call it out by name because I didn't want to distract from other things, but the cat was really entangled with the atom. But in order to best study entanglement, let's consider a pair of Stern-Gerlach apparatuses. And we are going to place one detector over there and one over there, so far apart from each other. We now start with an electron source that is like common for both sides of the experiment. And we are not emitting a single electron anymore, we are actually emitting a pair of them. And they are entangled. And what does it mean they are entangled? It simply means that they were created using the same event, or they interacted with each other. There's nothing special about this. It happens all the time in nature. So we then send one electron over there and the other over there. And these electrons, they are actually not prepared with any specific component of the spin. So they are effectively in a superposition of all the available spin values. And then they actually go through these magnetic fields that are oriented in such a way that they will deflect the electron up or down. And when they do, because the electrons are in a superposition, they actually acquire the value. They choose how to respond to a measurement at the moment of being measured. So in half of the cases, they go up. In half of the cases, they go down. It's sort of like, going through a beam splitter. And if we now compare the outcomes on the two sides of the experiment, we would actually see that the outcomes are perfectly correlated. Now, depending on how the electrons were created, this would either mean the values are the same or they are opposite, but there's always perfect correlation. I think for our use case here, we can assume that the results are always the same because it will just make the reasoning easier. So let's just say if on one side we see up, on the other side we also see up. So now what we can do is we can push them even further apart, right? And this experiment was done in setups where the detectors were kilometers apart. And we can time the measurement on both sides to the fraction of a second, like using an atomic clock maybe, so that they really happen at the same instant. And yet at the same time, still they produce the same perfectly correlated value, right? And now if they are really measured at the same time, there is not enough time for even light to travel between those two locations. Because if they somehow communicated with each other and managed to agree on how to respond to this measurement, then that's why we are doing it like this, right? So we can preclude this communication. And we know that nothing can travel faster than light. Because, of course, if something traveled faster than light, then it would go backwards in time. So we'll resolve this in a moment. For now, we just simply model this in Q#. Again, very easy, just a few lines of code. We have a pair of qubits, and we then place the first qubit in a superposition state. We use the H transformation. This is something that we already used to model the beam splitter. This creates a uniform superposition, so this qubit is equally likely to collapse to one of the two observable states. And then we do the C0, so the controlled knot between the first and the second one. And this just means that if this becomes 1, then the other one will also become a 1. But of course, the first one is in a superposition state. So we don't know whether we need to flip the other one or not. So we both flip and not flip. And so effectively, the superposition now infected the other qubit. And this is exactly what happened in our cat and the polonium atom. So they are now entangled. And then when we measure them, as long as we measure or observe using the same observable or the same measurement basis, they are both Z, for example, they would produce a perfectly correlated result. Otherwise, if I measure here in the Z basis, but here in the X basis, I will get zero correlation, right? So I just get randomness. We can run this in a code. So this is the same code that we had on the slide. And if I now measure this pair of qubits in the Z observable using the Z basis, we get, in half of the cases up, up, in the other half of the cases down, down. It's exactly what we would see in the lab. And if I measure in the X basis, I get 2 pluses or 2 minuses, right? So it's basically what we would see in the physics lab as well. Now, what is going on here, right? This is entanglement. Doesn't seem like that much, but it actually completely destroys our understanding of the fabric of reality. Einstein hated it. He called it spooky action at a distance. So there are 2 possible explanations here. The first one, the classical one, is the one that was championed by Einstein. And the other one is a quantum explanation, which is actually not an explanation at all, if you think about it. So the first explanation says, and this is what Einstein tried to prove, is that they simply carry hidden instructions. So they are basically like conspiring criminals. They pre-agree on how to respond to measurements. So they would say, if we are measured in the Z observable, let's both say we are up, right? And then they go their separate ways, they are measured, and they just say up. And if maybe they agreed for the X basis to say plus, right? And that's what they do. And this is basically what Einstein was after, like the solution that he was trying to promote. And it sort of seems to actually explain what is going on, right? The second explanation is a quantum explanation, which, as we mentioned, is not an explanation at all, because it sort of says, okay, they are entangled, and they will become instantly correlated, but since they cannot communicate faster than light, they really don't. And so it's like a magic, right? Like it's a bullshit explanation, really, to be honest. Now guess one which is the correct one. The problem is that for a long time, it seemed like this is a purely theoretical argument, because how do you actually prove which of these interpretations is correct? And as it turned out, actually, so Einstein was wrong all along, but he didn't live enough to be proven wrong. In the 1960s, John Bell, a brilliant physicist, John Bell, he was working at the time at CERN in Geneva, in Switzerland. But he actually came from, originally, he came from the greatest city known to the Western civilization, which is Belfast. See, I went to university in Scotland. So John Bell from Belfast, working at CERN in Geneva, he came up with this brilliant mathematical solution to the problem, right? Because he actually realized, and this is a simplified variant because the solution is quite technical, but this is a simplified variant. He basically realized that we can experimentally test which of these two is correct. Because he realized that if on the 2 sides of the experiment we measure using the same basis, so the same observable, so if it's like Z, right, it's vertical, then the difference between the two measurement bases is 0 degrees, and the agreement is 100%. And this is what both of these explanations basically predict. Now, if the difference between the bases is 90 degrees, so on one side we measure using the z observable, in the other we measure using the x observable, we have a 90-degree angle between those bases, or those observables. And then the correlation drops down to 0. This is, again, what both of these predict. But then he realized that you could actually measure using different bases as well, because you could rotate the magnets differently. And so then he imagined, okay, if I now rotate the magnets in such a way that they are exactly in the middle between the vertical and the horizontal, so it's like angled at 45 degrees, I could measure in the vertical basis on one side and using this angled basis. Now I have a 45-degree difference between the two ends of the experiment. And if they basically just pre-agree on how to respond to measurements, for this classical explanation, this correlation actually drops linearly. So we would have 50% correlation. But actually, quantum mechanics predicts that this correlation is a cosine of the angle, which is actually, for 45 degrees, is actually 71%. So all that was needed was actually to set up an experiment that was actually accurate enough to calculate this, because it was in the 1960s that he came up with this theorem, and at that time it was still a theoretical exercise. And over the sort of late 1970s, over the 1980s and the 90s, these three gentlemen, Alain Aspect, John Clauser, and Anton Zeilinger, they actually experimentally ran this, exactly what we've just discussed. And they've basically proven that the correlations that are exhibited by quantum objects are stronger than anything that you can pre-agree on, which actually means that then this explanation is correct, and there's this instant correlation that we cannot explain how it works. Now, mathematically, it's actually not that complicated, because we already said that a quantum object is described by a two-dimensional vector. Then the second quantum object, if I have two of them, that would also be described by a two-dimensional vector. And now, if I have two quantum objects in my system, in order to provide a composite overall description of the whole system, quantum mechanics tells me I need to take a tensor product between those two individual quantum objects, or these quantum vectors. And the tensor product is basically everything multiplied by everything, and that gives us a four-dimensional vector. So there's a single representation now for this entire system. But I can always go back from this into this representation, right? Because the quantum objects, they have their individual identity, so I can always go back and forth between these two representations. The problem is, once I have an entangled state, it has this four-dimensional representation. So when I entangle two quantum objects, they have this four-dimensional representation. But I cannot decompose this into a pair of two-dimensional representations, right? So here's an example of an entangled state in quantum physics. And if you look at this, you actually cannot find values of alpha, the values of alpha and beta that would actually solve this equation or provide this decomposition, right? Because if you look at alpha 1 multiplied by beta 2, that gives me a 0, which implies that either alpha 1 is 0, but it cannot be 0 because this would become 0, or beta 2 is 0, which it cannot be because this would become 0. So mathematically, from the perspective of quantum mechanics, once you entangle a pair of quantum objects, they cease to exist as individual entities. They only have the entangled representation. They do not even have a representation as individual object. The problem is that we can send one over there and we can send one over there, right? So we can spatially separate them. And yet quantum physics tells us, well, but they don't really exist as independent entities anymore. And that is why, when we measure them, they seem to somehow affect each other instantly. But from the perspective of quantum mechanics, they never did, because they never existed independently. They were just one system. And this is what we call non-locality, because it's sort of, it's not compatible with how we understand the fabric of reality at our everyday macroscopic level. And Henry Stapp called Bell's theorem the most profound discovery of science. Now, we can do very cool things with entanglement. And one of those things is the teleportation protocol. So we can actually teleport a qubit from one place to another. And this might be the last thing that you expected to hear about at the software conference, the teleportation protocol. So if you imagine, so this is the description of the teleportation process, a sort of high-level description. Basically uses entanglement as a resource. So it starts with Alice and Bob entangling a pair of quantum objects, so a pair of qubits. And then they can go their separate ways, and each one is protecting their little precious qubit, which is now entangled with the other side, right? And then Alice would like to create another, or she creates another quantum state, in this case M, and she would like to teleport this state to Bob. So what she does is she would actually entangle that new state with, oops. So she would actually entangle this state with her part of the entangled pair that she shared with Bob initially. So now it's like a 3-level entanglement, right? Except Bob is off and he sits with his qubit somewhere else. And then what she does is she performs a measurement. And basically from each of those qubits, she extracts a 0 or a 1, right? So she has now 2 bits of information. And she has to get those 2 bits of information to Bob somehow. And she needs to use a classical channel for this. And that is also why we cannot do this in a way that is actually faster than light, unfortunately. And she can do this however she wants. She can send him an email or I don't know, send or phone him or send a carrier pigeon or smoke signal, doesn't really matter, right? In the old days, she would put maybe a message on the teletext. And in any case, Bob needs to get those 2 bits of information, right? At this point, these 2 qubits, they are sort of destroyed, right? Because they've undergone a quantum state collapse at the moment of measurement or observation. And then Bob takes these 2 bits of information, and this is actually prescribed by the protocol, and he applies based on, 2 bits of information is a number between 0 and 3, right? So he chooses one of the 4 transformations that he should apply to his original qubit, the blue one, and it's driven by those 2 bits of information. And as soon as he does that, his qubit basically morphs into that yellow qubit that Alice had to begin with. So effectively, the net result is that A and B, they got destroyed, they disappeared. But M, actually, it disappeared from this side, and it now reappeared here, right? So we've managed to transfer a quantum state, and remember, a quantum state is described by a vector that is alpha over beta, so it's 2 complex numbers. You cannot encode 2 complex numbers into 2 bits of information, for example, right? So that it disappeared here and it reappeared here, right? And so we call this teleportation because it's like in the movie where the source was destroyed and it was then recreated on the other side. And now imagine that you are an attacker, right? And you would like to attack this communication channel, right? And steal this qubit that made its way from here to here. Well, there's actually nothing for you to attack because nothing traversed the space and time between Alice and Bob, right? The qubit simply disappeared here and sort of reappeared here. So that is teleportation. And based on this, based on entanglement, we can do other things. Like, for example, there is a quantum key exchange protocol that is based on entanglement, where basically 2 sides of the protocol can derive the same encryption key and then use it for symmetric encryption, right? And that protocol was developed by Arthur Eckert, actually in the UK in the 1990s. And when he did this, he called it quantum key exchange protocol without an associated element of reality. And if you think about this, this might be just most mind-boggling thing that you'll ever hear in software. So there you go. This is everything that I had. If you'd like to see those slides, then they are online. The demos are also online. There's also an implementation of teleportation there, if you'd like to look at it, and in-memory teleportation. And I think that's it. I used up all my time because the timer says this. I'm at 60 minutes, which is actually perfect because nobody will ask me any questions. So yeah. So let's close here. And if you'd like to chat about any of these topics, then just grab me afterwards. My recommendation is also, it's best to chat about this stuff once you've had 2 or 3 pints. Then the perfect topic to discuss. Thank you so much.